All right, we are live. We are covering some bonus lectures um, for class 8 tonight, the final class of SQL 101. Just sharing these with students. I've taught them previously, and they still add value in context of storing and managing enterprise data and tools that you can use that you may see in the enterprise for moving and managing and manipulating data, and then more about designing databases, which we cover in data a little bit more in depth in data engineering class. All right. So I downloaded that somewhere. All right. So storing and managing data. So why why I previously had this in SQL class, because it's really good overview of data that you would encounter in a job or in a larger enterprise. So, how do you, in a large organization, how do you take data from all of these different systems, extract it out, put it somewhere, whether it's a file store or a data lake or a relational database, transform it and clean it, and then load it into an analytical system that you can use for um, all of your analytical queries. So it is a huge task at the enterprise level. You have a couple of different types of data. The transactional data, this is like the business events in an organization. These are coming from all of your different systems, whether it's like a CRP, a ERP, or CRM. I'm getting my alphabet soup mixed up this evening, but it's an ERP that's like an enterprise resource planning where you can like order materials and store inventory and ship and everything out of it. And CRM is customer relationship management. So it might be like all of your customers or potential customers for the sales teams. Some of these organizations literally, I've seen it where they have 100 different systems running in their organization. And these are all different transactional systems that people work on a day-to-day basis. So it becomes a huge task, like, how do you bring this all together? And all those systems are producing business events. So if you're entering something into a system, an order, or you're receiving a new shipment, or there's a new sale or something like that, all of these are transactions. And you're trying to capture these and store them for analytical purposes. So that's where we talked about in this class a lot about taking all this information or taking all this data and turning it into the information that you need using SQL. You can do the same with a lot of transactional data from these systems because they also are in relational databases. But it's a big effort to do that from a whole bunch of different systems. Oftentimes, you're turning this into analytical data that supports decision making, reporting, querying, and analysis. And master data. So it's a discipline of your key business entities. Like, what are all your customers? How do you standardize their names and addresses? How do you create product lists for an organization and then use that across all of the data sources? There are a ton of, this lecture is all about that. There are just a ton of sources of data. And then how do you manage all of that at the enterprise level? How do you take it from transactional data to analytical data and supplement it with master data? So you have all these different sources. These are called online transactional processing systems because the goal of these is to capture those business events that we talked about. It's not really for analytical purposes. It's just trying to function as a system for whatever purpose. Like, you'd have an e-commerce platform. It's just intended to, list products on a website, have a web portal, allow users to purchase things, and so forth. So it's designed specifically for that purpose. You can take all these data sources and you use a process called ETL. So you're extracting data out of all these systems and then transforming it and loading it into some type of operational data store. This has traditionally been another database, but now you have data lakes and cloud platforms and all sorts of other databases too. Oftentimes, you're taking that most important information and translating it into a data warehouse or some data marts. These are like subject specific, where there's usually an enterprise data warehouse where you can go and get the source of truth for analytical data. So you're taking all this transactional data, turning it into analytical data that's fed into BI tools and reports and dashboards, or potentially even other systems for them to access. You can imagine how much effort there is, and you can large businesses have huge teams of people who do all this stuff under the covers even before it gets out to the user. Just taking all this data, turning it into analytical data that can be used by everybody. Talks a little bit about data management versus DBA. DBA is more like the direct functions of the database and performance monitoring, security, and so forth. We talk a little bit about that in data engineering class, but it's still mostly data management. So data engineers' jobs are, I think, really twofold. Is how do you manage data, and then how do you create systems that manage data at scale? So if you're interested in data engineering classes, it's all about building an infrastructure and processes that allow you to first capture all the data effectively, and then to do it at a large scale. So it takes all of these skills that you're learning here, and it just takes it to how you engineer data solutions. The data engineering classes I teach is like, how do you engineer data solutions that do that? Now, DBA is important, like setting up databases and security and performance and everything. That can be a little bit of data engineer's job too, but it's definitely like, how do you manage data at scale in the enterprise? And then you have some disciplines that help you out. You have data governance, which is quality control discipline. It's usually organizational effort for managing, using, improving, monitoring, and maintaining data. Who needs data governance? Organizations that need to prevent sensitive information from being accessed, or it's like really important for data to be accurate, like financials are always really important to be accurate, like accounting rules, or if big decisions are being made. Data governance is important, like how do you define certain metrics? How do you define data quality? Like, is there a lot of garbage in your data? If so, like, how do you clean it up? Data security is huge. Who can access it? Or, in the health industry, you have HIPAA and all sorts of privacy policies. If you have a data breach, it costs businesses millions of dollars, and then you have to notify everyone, and there's a whole reputation, degrade in reputation from all of that. So it's this huge discipline that is all of these different disciplines within data governance as one large discipline. And then data stewards are usually people within an organization. They know the data, they know the systems, that ensures these processes are followed, that data governance is set out for the organization. So this is really like one, if you work at a big organization, a lot of like smaller organizations won't be as mature and they don't have this type of governance. But if you work at really big companies, there'll be a lot of policy and data and process and not security as much. Security, yes, but all of these disciplines in place to help make sure data is secure and of the highest quality, and people can trust it, and it's consistent across organizations. Kind of those dimensions of data quality that we did in the cleaning class. You'll see data dictionaries. A data dictionary is a collection of sources, names, definitions, and attributes about the data elements that are captured in a system. So this is really common in a relational database. So see what source the data came from, what table in that system, what the name of it was in that system, and then the destination. So the destination table, that's probably like your analytical table, what column it is there, and then what transformation did you do to the data to take it from the source data to the destination data to your analytical data. So for example, maybe you got some information out of a spreadsheet, contact spreadsheet about marital status. You put it in your data warehouse in the contacts table. It's now called marital underscore stat. And then you converted all of these, whether it's single or S or SNG, you converted that value to S, or maybe you converted it to M or D or W for widowed, divorced, married, or single. So it says, especially in the big organizations where data could almost come from everywhere, the context of where data comes from matters. The data dictionaries can provide those guides on where that data came from, where it is in your data warehouse environment, and then how it was transformed once it got there. So really important on keeping track in the context of where data comes from in an organization. And measuring data quality is always important. So all the things that we talked about, we learned some skills, SQL skills on cleaning data. But as we saw, sometimes errors or incorrect elements are present in your data. It's important to be proactive and clean that and periodically test for inaccuracies. So I've seen in organizations what they do is they create their own tools, or they have tools that assess data quality. So you'll create a bunch of rules, you'll set it on maybe a database table, and that software will go and see things like how many nulls are there, how many outstanding or like how many invalid values do they think there are, how many values seem out of range. I think I mentioned null values, invalid values, and so forth. It's continually assessing data quality so you can proactively make those changes. And you could have there are lots of companies that do metric dashboards. So they create a dashboard just so that they can measure these data sets and issues that are with it. So things such as missing, incomplete, or redundant entities, duplicate and entries in a relational database table. So in theory, it shouldn't happen, but in reality, it does happen within these systems. And then when you're extracting it, when you put it in analytical tables. So just at the end, you could do data quality with Python. There are libraries that do it. I don't know if you learn about that in the Python class coming up. But it's possible you could do it. You could read in your data set, run a Python library on it, and it'll create all these stats and give you recommendations on what to clean up in your data. So this is really all about data in an enterprise, particularly an enterprise with lots of systems, different types of data sources, converting it using ETL to convert it to analytical data, how they manage data, and some of their practices for data quality and data assurance and documenting data. So if you work at an enterprise work at a large business or an enterprise that really values data, they almost certainly have these, you'll see these things, or they'll have these things in place. All right. So that's one. There are a bunch of tools for data manipulation. So taking this data, we saw in here where you take all of these data out of systems, and then you're extracting it, you're transforming it the way you need, and you're loading it into some source for analytical purposes that you can reuse for reports and dashboards and everything. Well, there are a bunch of tools for this. One of the challenges you have when you're trying to do this at scale is writing code for every single instance or every single business rule and every single instance of data out of all of these different systems. And then ultimately, like, how do you manage all of that? You could have a business rule, you're calculating a metric, and you do this in like 50 or 100 different pieces of code. But what happens if that metric changes? Like, then you're going back through all of your entire code base, all these SQL scripts, possibly, or Python scripts, and then you're trying to find all the places where you need to change it. So it becomes a huge task, not so much at a small level to be able to manage like all of these scripts and extractions and transformations and everything, but at a large level, being able to manage that. And that's what these tools are all about. They help you manage it here at the enterprise level. So we talk about ETL in the data engineering class, and we talk a little bit about tools that will help you do that. So in this class, you learn about those things. You can use Python for it, but then again, you're still writing code. It's useful for really high customization for like your initial pipelines that you create. We call them pipelines, that you take data from the start, you transform it, and then you load it in a pipeline. So it's like a processing pipeline. You can do those using Python, often a good way to start. But then often you're using a tool like Talend. Talend's an open source ETL tool where you can take that code, or you can build a visual pipeline instead of creating the code. Or you can just transplant this code straight into this tool, and then it'll help you manage all of the code. Dataiku would be a data science platform. So if you're doing data for data science, you can take data, you can create pipelines in there to create your predictive models or your machine learning or AI models and export them out of a platform like that. So they're really workflow tools, so you don't have to like write every piece of code and all the data transformations that it takes to go from start to finish. They're cloud storage platforms. There are three main competitors. All of these have similar tools, but they'll contain ETL and workflow tools that help you automate data. I also teach a cloud database, not cloud database, a cloud data engineering and API class. So it uses REST APIs, and you extract information out of those. So REST API is just like a connection to a system where you can connect to it with a program. You can extract data, or you can tell the system what to do. You tell the system what to do. Usually in data science, you're extracting data out of it, and then you put it somewhere in the cloud platform where you can use it for analytical purposes. In that class I teach, we use Microsoft Azure, and we create a machine learning model in that class. So you go from start to finish, from extracting the data in the cloud platform all the way to building a machine learning model. So cloud storage is really valuable, especially for data at scale. And we talk more about that in just my intro to data engineering class also. NoSQL, it's an alternative to relational databases in SQL. It is a document stores. That might not really mean a lot to you. I would keep it in the sense is instead of a tabular format, it's in different programmatic formats. So you'll learn more about this in Python, but you can have different types of data structures that aren't necessarily just tabular. You can store them in specialized databases, particularly NoSQL databases. And we used to have a class project in this class, but not anymore. So I always say one of the most important things to data engineer is you don't have to do everything with a hammer. Not all jobs have to be done with a hammer. The more you know about your tool space for a particular kind of work, the more efficient that you can be and the more effective you can be at engineering solutions. So Python's really handy, but you don't have to use Python for everything. You could use cloud tools or different technologies or pipelines within cloud and so forth. So if you know like the tools in the tool space and then what are most popular, it can help you tremendously with doing work at scale. So more of an engineer's job, but just sharing that with you. If you have interest in taking the engineering classes, data engineering classes coming up. We talk quite a bit more about it, different types of databases and tools that you can use for both traditional types of analytical processes and then big data processes and machine learning and AI. Use different types of technologies for different types of work or more effective different types of work. Yeah. Did talk about ETL. You extract out of systems, you transform and load it into some place, to some type of storage. You load it into an analytical data mart for analytical purposes. Maybe that's for reports or dashboards, but they're also data stores for predictive models or machine and AI learning models. Machine learning AI models, sorry. And then that's where your output is, your analytics. So it could be a dashboard. It could be an AI. We're doing work in creating AI agents. So it could be an AI agent that does some tasks, or it could be embedded in a system. It could be a lot of things. So it's ETL, and you have a bunch of tools that can help you out with ETL. Large organizations will almost certainly have some type of tool to help them do this at scale. These are some of the more popular ones. These are a little while ago. There are a lot of cloud tools out there now, but there are a lot of independent tools that can help you out. If you see, one of them is SAS data integration and data management. I never personally used it myself, but often these BI tools will have some type of connectors and ways to connect and extract and transform and load data for analytical purposes into their platforms. You can also create these all using Python, using supported libraries. I know for sure you learn about the pandas library in Python, and pandas is why it's good to take this class first is pandas is a library in Python where you can create tabular data structures and you can do all sorts of data manipulation on it. So you'll be covering some of that in the next class, but that's kind of that Python's version of SQL. And then you could even run SQL style queries on those. They call them data frames. But you can do a lot in Python, which you'll learn about in the next class. I do talk about Talend as a tool where you can do visual workflows instead of writing code. The less code that you can write, generally the better. There's a demo inside of that. And then I talk about Data IQ, the steps to engineering a data science workflow. Wish I don't have a video of it, but I do have somewhere else. I have more steps and instructions on how to do it. But I should put a video in here. Try to put a video in here so you can see how you would take data, extract it into this data science tool, and you create a project. And then you could do things like transform the data you need. You have visual workflows and visual prep. Then you could build these models on top of it, then review those models, and then deploy them and monitor their performance. So it's like an all-in-one data science platform. It's a little bit different way of how you use data, but still the same idea in doing it visually instead of writing a bunch of code for it. But this is for data science specifically. NoSQL, has briefly mentioned that, but it's a way to store, basically do all these things we learned in this class. We learned about being able to store and manipulate and manage data, and then writing queries to retrieve data, and then a bunch of different processes and some advanced SQL structures that you could use. These are really, when you say NoSQL, it's just all the other technologies that store data, but they don't store it in a tabular format. They'll store it in what's called a document. You'll learn about that data structure in Python. You can do key values. So you have, it's like a big lookup table. You can have a key value, and whatever your key value is, you have a corresponding, your key, you have a corresponding value to it with it. And then column families, somewhat similar. It's more of a dynamic structure, but I was just trying to give you a flavor of it. Your SQL technology is just a part of it. And then you have all this analytical data that you do with NoSQL technologies that you learned about in my data engineering class. And there are some technologies here, relational database technologies, now that help you create data warehouses or data marts or different type of analytical data structures that you can use. There are lots of these now, particularly in the cloud. So there's just a short list of these, just the awareness that if you're a data engineer, that SQL is just the tip of the iceberg. Still widely used in all these transactional systems. SQL's like never, as I said at the beginning of class, never really going away because so many people are familiar with it, and you build so many applications on top of relational databases that there's always going to be like relational data that you need, and it's super valuable to learn SQL. But now they're all, as a data engineer, all of these different tools or databases that you have for specialized purposes that may be a better tool than relational database. So really, data engineering territory with this, and then some of the structures goes into a brief description of all of these different types of structures. If you find them interesting, you can dive deeper into it, or take my intro to data engineering class. There's a demo of how it works. So it's a database that you can query. It has a different syntax than SQL. You don't write it like a SQL query. You write a different style of query to be able to direct that database in the same way you direct that database to update or delete or select that information that you need out of it. But it's in a different structure. So you give it different commands than you would in SQL. And then cloud computing is important, especially in this day and age of just big data and so much data that's being stored. It helps with the scale that you need to be able to store all of the data. So just being able to store all this data is important, but then to be able to process all the data and then turn it into information or use it in AI models. Traditional computing, it's really hard to do with just like your computer on your desktop. Cloud computing allows you to take all sorts of these huge computers, basically a huge series of computers, and then be able to use that processing power and scale it as you need. There's services that do it. Amazon, Google, and Microsoft particularly, they all focus on data. They are up most of the time, so you don't have to worry too much about failures, although there's a recent Amazon one. And they have lots of these built-in tools that we talked about to help with data, and they improve all the time. The more and more organizations use data. So yeah, they all offer similar tools. These are all the relational databases of the cloud platforms you use. And then enterprise services. So in Google Cloud, here's the different technologies that are used for different purposes. So often there will be some for storage. They still have SQL databases like MySQL or Postgres. Relational databases aren't going anywhere. But then they have some tools for NoSQL and then big data processing and real-time data processing. And then some additionals at the end. So I only have one more deck. I'll cover it, and then we'll take a break. So database design, I have taught this every single class until this one. And I took it out. I go back and forth on whether I should include this class, but I think that it can be included. I think it can be included in data engineering instead. So we talk about how do you build database modeling is how do you build a database. And we learned in the other lectures there are two types of databases you can build. You can build an OLTP database that's focused on transaction processing and systems and how to capture business events. That's really not the focus of this class, using SQL in this class, although now you have some of the skills to be able to potentially do that. But you can also use these databases to build OLAP models. So these are your data warehouses. And you can build these data structures and store data. When you take that transactional information and you transform it, you can store it in a way that you can use it for analytical purposes. This is an OLAP model, an online analytical processing model. This is what you'd often see in your data warehouse. It stores like a running history of your business events, summarized business events, and then you can easily access it so you don't have to do all these transformations all the time. So the purpose of database modeling is usually in a traditional sense, you're gathering in tech, you're gathering required system requirements, functional requirements, bringing these all together, and then designing a system. Well, not always designing a system. Maybe you already have a system, but adding some functionality to it. But on the back end, you also have a database consideration. So how do you take all that data that the system's producing and then capture that those business events effectively to be able to run and manage your system. You have a few different ways you can take these requirements and model it for what you need in databases. So you can have like a really high level one. So maybe there's something like your customer. You talk about your customer. They place an order for a product. So those would naturally lead to three very well-defined tables. They're usually like your nouns that you have when you're gathering requirements. It's usually a person, place, or thing. So you have your customer placing an order. You have all your customers stored in the customer table. You have all of your orders stored in the order table for all of the products potentially in your catalog. So like the Sequila database, you had things like film, your customers, your locations, your genres, your inventory. All those things are like when you're designing this system or you're designing these databases, like things that you want to capture within like that video rental system. This would be just the same thing. When you have it at a high level, then you start defining all of the columns that you want in the table, what you want to capture. So the customer, maybe it's just name and email to start. In your order, you have an order ID that uniquely identifies the order, and you have order date. And of course, maybe you'd want to expand this to like certain qualities about the order. It's like describing the order, like the adjectives. So maybe you would do like order type, order amount, the total order amount. You know, have some time, like sometimes you'd have stuff like tax on it and delivery fees, whatever you would decide to put in your order table. And then that's how you design your tables into SQL code. So you're gathering it at a high level, what you need it to do, at a logical, like what you need out of it, and then it's your physical model, how you actually implement it within the table. So we have transactional and analytical. If you're designing these two databases, they have very different purposes. OLTP is like high performance. You're just trying to capture these things, and you're capturing like simple updates to customers. You're trying to have it as high performance as possible to be able to handle like all the people coming into a e-commerce website. You have simple updates. Maybe you have updates to customer information, new customers, where you're deleting the customers out of the database. OLAP has very different purposes. Maybe some of those customers you deleted, you want to keep those for analytical purposes. So you'd extract that information while it exists, you transform it and store it for analytical purposes. So you do that for queries, forecasting, so forth. So the database, yeah, so you're designing OLTP because you can only handle so much data. And then on top of it, analytical databases. If you design these data models, they have their own workload. So it's good to separate both of those for performance and scalability and consistency of data, let alone having two very different types of data. So there are different techniques that you can use. We talked about like requirements and how you would design tables, but you can use different techniques to design each type of table. In analytics, we have often have a dimensional model, and we'll see how this is good for analytical purposes. But this is how you would do a data flow diagram. You'd have your customer, and you do things like confirming order details, specific build details of, I guess, maybe they're ordering some type of product that has to be manufactured at the factory. Factory does that, they deliver it to the customer. It's kind of like your steps in your workflow. And then relational model is like it sounds, your relational table models, how the tables relate to each other. And data flow, how data progresses through the system. So yeah, this would be a data flow diagram saying like the customer confirms order details, specifies the details of the build, the factory creates the product, the build, and they set a delivery date to go out to the customer. So it tells you how data flows through these tables and systems, and then your analytical data mart, or your analytical design for data, for those data purpose or for analytical purposes. Okay, so there's a lot you can go into with OLTP modeling. We do cover this now. We do cover it now in data engineering, because one of the functions of a data engineer is to set up databases or processes or systems that both captures and manages data and then does it at scale. So it is a data engineer's job, not necessarily to set up OLTP databases, but to understand OLTP databases that they're working with underneath the scenes. How data flows through a system is really important on figuring out how or when and how to capture it. Entity relationship diagrams. So your entities are like your tables, your attributes are your fields, and then you have the relationships between these are all different types of relationships that you can form between tables. Maybe it's a one-to-one or a one-to-many. I have an example in here on how you would capture, this is a project I worked on, but how you would capture business rules to create an entity relationship diagram. And then this is a database that we created out of it. So you can see it's the system is a record keeping system for repair shops, so that you could have services there and you can take pictures of it and document the entire system. But you'd have services, you capture invoices and all of the repairs that happened in the shop. You could take pictures of all the repairs that happened, what type of car or boat or whatever your repair subject was. Could be even a home. Who is the owner of this? I think that was the vendor, and this is the owner of the store. But then you have the relationship between this is the owner of the repair subject. But anyway, you can see how you gather a bunch of requirements, and then you design a database that needs to do all of these things. But ultimately, you have to take this information, convert it in a way, store it in a way that's useful for analytical purposes. So if you work at a big organization, oftentimes they will create data marts or data warehouses, and they will design these types of tables that are really easy for analytical purposes. So instead of having to figure out what 5 tables you need to bring together to be able to create a query, like we did if anybody used the Sequila database, oftentimes you have to go through multiple tables, the joins, to be able to get to the table just to get to the table that you needed. Instead of doing this, it becomes very straightforward. You have your facts or your business events, and you have things like employee information and product information and your time dimensions. So like your months, your days, your weeks, different stores. And you can easily write queries like, give me the quantity sold at the store in Omaha, Nebraska last week by a certain employee who was working. So it becomes like really easy. These are all just one straightforward joins, oftentimes left joins to the fact table, but you would just join these and it makes for very straightforward analytical queries while storing these in an analytic, capturing all the business events in the format that you need for analytical purposes. So there are a couple of, that's a duplicate slide. So there are a couple different ways you can design it, but star schema is by far the most used. And normal forms. So this is a debate that I have on still including normal forms, because normal forms, and to some degree these, because as a data analyst, being able to look at a schema and being able to design a query like this is still important. So you could see like what the keys are and how to join them all together and their relationships to get the information that you need. And then even this. So if you're designing a database, understanding normal forms. So normal forms are the principles of how you should design tables. So almost always I just use first normal form for analytical purposes, because I'm really just inserting a bunch of records for analytical purposes. Like this is stock information, Microsoft on each day and what the closing price of the stock was. So the first normal form is just that every value must be a single value only. You don't have multiple values in the same column. All of your rows, you have a primary key, and then all of your rows are distinct based on that primary key. That's why we design tables without any duplicate. We try to design tables with a primary key and without any duplicates in it. So if you see the key here is symbol and date, this one's always unique. So this is Microsoft 9/7/2013, Microsoft 9/8/2013. These are all unique, even if symbol repeats or date would repeat, the 9/7 would, but the combination of symbol and date makes all, as the key, makes all of these unique rows in the table. And then the order of these it doesn't matter what order the rows are in or what order the columns are in. You'll always get the right result with SQL. So it's just basic design. I would try to always use the principle of first normal form when you're a data analyst. It's basically just having a primary key and unique columns in a table. And then there are other advanced normal forms like second normal form. It's just breaking this down so there's less redundancy. There are different ways that you can do that, and you can get very advanced with it. And in the past, I've asked people to take a look at the Sequila schema and identify different things in the schema. So this is one thing I'd consider putting back into this class, probably mostly to get people used to reading schemas and understanding them as a data analyst. Not so much to build the tables, but to be able to understand them and develop queries from them. All right, we covered it in an hour, just about an hour. Thoughts on this? Did anybody go out and get their own schemas for Sequila and then write queries on the database, or did you do this you can do it for the world database too. The world database is a lot more straightforward because it's just like 3 tables with, I believe, this city is in the middle of it. But to be able to do this Sequila, to write queries on the Sequila database, you would almost you'd need something like this, and I can't. It seems like in my brain I included it in the first homework, but maybe not. Anybody find or anybody use any schemas, or would they find it useful learning more about this in class? Just tossing it out there.
I mean, I've done some of this stuff before. I mean, I kind of feel like that's what when I'm doing the Power BI stuff, right, and figuring out how things are related.
Yeah. Yeah, in Power BI, you're creating. Oftentimes, you're importing tables, and then you're creating all these relationships in there.
Yeah.
So, like, you're creating your own little data model underneath. Usually, Power BI, you create like your own data model by connecting a couple tables, and then it creates like that reusable data source.
Yeah.
That you can use in different dashboards. I kind of consider you can create like little mini data marts in Power BI, which I think is useful too. It doesn't necessarily have to be like this dimensional data model with a bunch of code and ETL. It could be just like a Power BI data model where you bring in a couple different tables and you define it for a specific purpose. It's like a data mart.
Yeah, well, it was kind of handy actually. Today I had created it, and as like the queries or as my visualizations changed, and I was trying to do more, I was able to go back to one of the tables where I had only pulled in a couple of columns, and then pull in all of the data in. So that felt kind of good because I thought, oh God, do I have to reload the whole entire table? Which in essence I did, but it was a really easy step to do in Power BI. So that was helpful in terms of the process.
Yeah. Yeah, the only thing I guess it depends on what tables you're loading, but the only thing I'd be concerned about with those Power BI models is that the tables are capturing data in the way that you want it to be captured going forward. Like it captures data the way you need it to be captured.
Yeah. It's a pretty small shop, so there's not a huge amount of data, but yeah, there were lots of alerts saying this might break your other queries.
So I do consulting for, I'm doing bigger projects now with CAN, but traditionally I've done small to medium sized businesses, and none of them like have data warehouses or anything like that, but they may have databases like this. So I bring data together for them in Power BI or something, or I'd set up some extract that you could use for reporting. So you do a query like this and just provide an extract out that you use for reporting purposes that you can count on. And I think that's fine at a small scale too. We're just bringing a couple tables together, capturing data and bringing a couple tables together. Then they can see data like they never have before, in a way they never have before, just by doing that. Yeah. That's kind of what I like about it. It pays less, but it's kind of like the low hanging fruit. Kind of easier work to do something that somebody has never seen, and just doing it for the first time and bringing it together in something like Power BI that they already have. And sometimes they'll get that client started down the path of like, oh, we want more of this, we want to do some more of this. How do we do that? And then that's where I bring out the Cadillac solution. Maybe not Cadillac solution, but I say, give them advice on how they could do more of it. Try to do it sustainably. Think ahead. Do it sustainably. Thinking like a data engineer or data architect. All right. So that's lecture for tonight. I'm going to end the stream. And I'm just going to leave the rest of the time